is a capacitor. So let's bring capacitance in the equation. The capacitance from what we just said initially, let me give you that. So let's look at something here. From here, actually, capacitance, which is a constant of a particular capacitor, capacitance will be equal to the ratio of your charge per volt. Okay, so the charge that you have, if you have these charges, okay, for that material, how much voltage the charge, how much of the charge constitutes, let's say, one will give you one voltage, okay? That will be a property of that capacitor. So by definition, this is it, okay? It's the charge. So how much charge you can have, the amount of charge you have on your body, and then its corresponding voltage that it gives. So that is the property of the capacitor. Some may have a small charge and then be able to, we have maybe small collection of electrons on it, but the voltage may be high. So then we say its capacitance is high, okay? If it has maybe a very large collection of charges, but the voltage is low, then it has a low capacitance, okay? Right, so that is the ratio. This will help. So putting this in the equation, we want to have an expression that we can have capacitance in, so that we get an equation to look at how this. So this is more or less a discharging capacitor. Okay, so it is discharging, it's not discharging, it's not charging. Right, so from here, from this, okay, if we substitute for V, we're going to have what? We want to substitute for V because we want V to be out of the equation and get Q in there. So once we get Q, we can then differentiate this equation and then sort of connect charge with time, because as it's discharging, it is discharging electrons against time. Okay, so that's that equation that one will come into the picture. So in this case, we're going to have, if you substitute for V, the same as V is equal to Q over C. So if you put that here, we're going to have the Q over C over R dt. And this is what is going to give us the Q is equal to Q over C R dt. So let's bring Q here. Then in that case, we're going to have Q, the Q is equal to 1 over CR dt. So this is what we are having now. This makes the equation very simple to handle now. So all we need to do is we have our dt here, and the Q here, and our Q here. There's constants here, another constant here, so we are good to go. We can integrate this from Q initial to Q final, okay? And then we have our Q here, the Q, alright? And then we can also do the same thing for this. I can integrate with respect to T, from our T initial to T final, okay? 1 over CR dt. Right. So let's see how it goes. Right, so yeah, so I think that there was a small mess up here. Let's look at the mess up where it came from. Okay, we have our Q over C here. Q over C. We substituted Q over C here. Q over C here will give us this. So Q coming here will be over. It's not going to be times. So that is where the mistake is. So this is going to be 1 over Q. So all that you need to do, just be careful with the letters and everything. Just arrange them as, when this one goes in, it's not going to be multiplied. It's not going to be times, it's going to be 1 over Q. Okay, so this side becomes 1 over Q. Let's clean that. Okay, so this is 1 over Q. Right, so we are good to go from here. Now we can integrate this. If you integrate this one, it's the same as writing Q minus 1. If you integrate this one, you add 1 to it, it becomes what? Q minus 1 plus 1, okay, over what? Which is what the answer that you get in here will not give the answer. So here it's 1, 0. That will make it well defined. Okay, so this is not possible to differentiate by this method, because this will make it well defined. So it's not possible to differentiate by this method. It means it's not going to define. So we'll look at another method. Just look at this carefully. It's 1 over q. We know from our integration and differentiation that when you have 1 over q, it means the lane was used somehow. You can look at it. You look at it whether the down one is the equation and the top one is the differentiation of it. So if you differentiate this one, it is this. Okay, you get 1. If you differentiate this one, you get 1 minus 1. It will give you 1a. So since this one is there, then it means. So you see how we don't just straight away do anything. You try to go step by step. See, trying to go by the normal method, this will not work because this will be 0. It will make this equation ill-defined. So it means there's another way to deal with it, and that is by using recognition method of the natural log. Okay, so that will mean this portion of the equation, will drop to natural log of q. Okay, then we have our q initial, q final. Okay, it's equal to this one, and this is constant. This is constant, and this is going to give us this. There's nothing you want, so it become t. Become t like that. T final, t initial, and we have 1 over CR. Okay. Now from here, we can do that. We can simplify this one. So let's say q initial. If let's say this is 0, so or let's put in the values like by the same formula. So we're going to the natural log of what q final over. So it's going to be this q final minus natural log of q initial is equal to. This is also going to give us 1 over CR t, because time 0 starts from 0 to final, so t final. Okay, right, and then this one can be expressed as what? Natural log of what? Q final over q initial is equal to t over CR. So these equations, you see them in the books and you are frightened, they can easily be derived. So this will bring us to this point of the deriving. Yes, so this should give us the answer. But let's not forget that before I put it. No, this is discharging. Now, if it is discharging, it means the Q, the T, okay, with time, the charge is reducing. So this actually will become minus. It's actually supposed to be minus if you take to factor the direction, okay? So if this is minus, going to have minus, you can let the minus sign. So this should be minus, the minus sign comes here, okay? The minus sign comes here. Because it will be here, it comes here, and then the equation, we're going to have this as the equation, okay? Now we can take natural log, antilog of a natural log, okay, or anti-natural log of this side. So this side, we take anti-natural log and then we get the equation. So the expression will then become this. This is what I mean. Let me make that so. So this what we have here as that. We have here as natural log q final q initial minus t over CR can be rewritten as, let's take natural log. So it's going to be q final q initial is equal to e negative t over CR. Okay, right, now this you can also rewrite as the q final is equal to q initial e negative t over CR. Okay, so when the capacitor is discharging, this would be the relation. It's okay, the charge that is going, okay, as according to time. This would be a relation to use for your calculation. Now let's look at the charging capacitor. So So the circuit, this is our capacitor. Let's say this is being charged by a cell. So we have that. The cell is charged, so we have load in here to regulate the current flow as a resistor. Okay. Right. So that our graph like that. So it's going to start charging. This side is positive, this is negative. Okay. Right. But like we said, current electrons actually move from here to this side, and then maybe it's positive, maybe it's negative. So in the same way, you can look at it negative. In the same way, you can look at this as positive coming here and then making this negative as well. So this is the direction of current, and we call this conventional current. That is how we are defined conventional, because we have agreed that is the direction of current. We have agreed that when electrons are moving this way, current is moving in the opposite direction. This was from the initial this thing that was made by our predecessors. Okay, so that is the point. So when the circuit is closed, when the circuit is open and it's closed, okay, so then the charging will start. Okay, to start charging goes up, and then we'll have this decreasing like that. Now let's look at the relationship for, or the equation that will relate the various components for a charging capacitor. So this is just a simple circuit for capacitor. Just to illustrate how things will go. So for instance, we already know from the same here, okay, we can say V is equal to I over R, and then say what I is equal to V over R. I is also the same as the Q over the T. This time is building up, okay, over V over R, okay, and then we know our capacitor is what your charge per voltage, okay, and how much charge. If you have small charge, you can give it, you can let it assume a bigger voltage, then your capacitance is high. Alright, so that's the capacitance relation. So that definition, capacitance definition, ratio of your charge to your voltage. Now this can also be written as V is equal to Q over C. Now we substitute this one in for the equation, then we are good to go. But let's look at for this equation. This is R, this is our capacitor. Okay. Now this is E. You realize that E will be equal to what? E will be equal to the voltage for the capacitance. Okay. Plus what? Voltage for the resistor. Because when this is closed circuit, for a closed circuit, it is said that the voltage, the EMF should be equal to the voltages across the various components in that circuit. Because this EMF will gives all of them the voltages, or the potential differences. Okay, so the source must be equal to whatever happens in the closed circuit. Right. So that's Kirchhoff's one of Kirchhoff's laws. The other one is you have a fixed point like that. This is current coming in should be equal to current leaving at the junction. And then the other one is in the closed circuit. Okay, this is my EMF. Okay, this potential. This EMF must be equal to this and that. Or when the sum of the various EMFs, okay, should be 0. Okay, so if you add all the EMFs, should be 0. This is the source. So if it is positive, these ones are taken from it, so we integrate. So you take a direction, and the direction can be used to do the calculation. So from here, we can have the voltage that we're talking about here. Let's put a proper equation here. So this voltage for C, we will relate this one to this to find the equation. So this is the voltage for the capacitor. Okay, the voltage for the capacitor. Okay, it's the current through the capacitor. Okay, and of course the resistance is offering. Okay, the resistance in the circuit as what is in the circuit, what is so let's see for VC, in place of VC here, let's see what we can do. VC will become what? E minus what? VR. Okay? It's equal to IC or I current R. Okay? You know, it's represented to the current, the capacitor. Okay? That is what is happening. Now, this is the same as saying I is equal to E minus VR over what? Your R. Because this will become that. And this is the same as the Q. The T is equal to E minus VR over R. This is where the equation is. Okay? Right, so this is what we're going to have. Now let's do some substitution for the capacitance. Let's bring capacitance into the equation because we want to see how capacitance together with charge and time are related. Okay? So that we see how the equation can work. Okay, so capacitance is given by what? Your charge per voltage. The charge that you have, its voltage, corresponding voltage. So we can substitute this one. So this is the capacitance of the capacitor. Okay, the same as V is the voltage across this one. Okay, with the voltage across this one, its resistance, the resistance involved. Okay, and then the current that is, so the current that is flowing through this IC must have its voltage VC. Okay, and then of course the resistance will be as we have mentioned up. Okay, right, so this VC this is VR here, because that is going to be subtracted. Okay, now this is VR. Okay, so the VR, of course, the current that is going through R will be initially, of course, at the end, on average, opposite to be the same current that is going through this. So we can then substitute this charge over voltage, okay, into the equation to get the expression for the other one. Right, so this will be an expression for with respect to capacitance. Okay, you can do the substitution, you still come back to it. But let's look at, so this will give us an expression, at least we have the idea of how this goes. Now let's look at it where we are looking at the properties for the resistor itself. So the resistor itself will have V, R, will have I, R, and then which one is left? Okay, the resistance itself is R. Okay. Of course, this one, the resistance, if we are looking at with respect to this one, is the resistance for the capacitor. Okay, that is it. Now let's look at another picture where we are looking at the parameters for the resistor. But remember, the current IR will be the same current for the capacitor, because they are in series. Okay, when they are in series, the same current will flow through. Okay. Right, so let's look at it this way. So in terms of the resistor, our same method here can be V is equal to I, R. So V is equal to the V of the resistance of the resistor, I of the resistor, then we have R. Okay, but from this equation, the EMF, VR will become what? E minus VC. So we can put in place here, we can put E minus VC is equal to I. Let's just make it I for purposes of simplicity, the same I that will go to R. Okay, then it means IR is equal to E minus VC. So I will be equal to E minus VC over R. Now our I is equal to dQ over dt, which is the same as E minus VC over R. Now let's bring the capacitance into the equation so that we have capacitance is given by this. Bring the capacitance into the equation so that we have an expression for taking care of capacitance and then time. Now if we do that, we can substitute VC. This is VC, yeah. So the charge that is coming, the capacitance, okay, and then this is the voltage that we have here. So from here, V is equal to Q over C. Okay, it's the same current that is going through. Okay, V over C. V is equal to the VC. You know, this is capacitance, so this is the VC. Okay, capacitance, so this is the VC. So, and this is the charge, it is discharged, the capacitor is discharged. So VC is equal to Q over what? This is equal to Q over C, the capacitance. You can put that here. Okay, so that will be the Q, the T is equal to what? E minus what? Q over C over R. Right. Now we know that at the maximum point, when this is fully charged, okay, when it's fully charged, the E can be related to the E can be related to our C, of course. There can be a relation between that. Now let's see how that will come into the picture. The voltage here is that. So let's say in that case we will have what? Total charge at the point that the whole charge is gone. Then can you kill the voltage now is now on the capacitor, so it becomes what? E, and this is the capacitance. Okay, so that Q is equal to what? CE. So here, that is when it is full. Final, Q final will be equal to CE. You can have this expression somewhere. We'll come to it. So in place of our Q, you can put CE there and then factorize the C out. But we'll come to that. So let's see. So this is what the expression that we have now. Let's see how we can simplify that. Alright, so from here, let's go on. So we're going to have what? Let's simplify this equation. This is R. So R will come like that. So we have R dq dt is equal to E minus Q over C. Right? Now let's get rid of the fraction. Let's multiply it by C. So we have C R dq dt is equal to E minus Q. Okay, of course this will become C because C will multiply this E too. So it becomes E minus Q. Okay. Now at this point, we have the Q here, so let's bring Q there, and then T goes to the other side, so that we can sum both sides. Okay, so this is going to give us the Q. So let's bring Q here. We are bringing Q here. Q become so plus, let's say C R crossing Q T, so this becomes Q plus is coming in, or let's get rid of let's go to CE. Now let's look at this point. Right, so if you look at it from here, if you bring K here, it's minus, it becomes it's minus. Minus here, it will plus, but it will not make this equation simple for us to integrate. So let's look at another way. If we examine, so this will not make it simple for us. Let's see. Let's look at another way to simplify it and to make it very simple. If you look at this expression here, CE here, CE, like we said initially, I said what we have done here is to make use of it. So this is the Q final. When the capacitor is fully charged, it becomes the capacitance times the EMF, because everything has gone into the capacitor. Everything from the cell has gone into the capacitor. So it becomes the capacitance times the voltage, and that gives you the charge. So we can put in place of that, we can put Q final here minus our Q is equal to our dq dt, and then we have our CR here. So this is the equation. Now if we have this, we can now send the equations over. So we can just say CR is equal to dq is equal to Q final, Q initial. Okay, dt was dividing, so it will come and multiply dt. Okay, so you can interchange, you can bring this one here and then send this one there, so that you're going to have what 1 over Q F minus what Q dq is equal to 1 over, that's also going to be this going to be 1 over CR dt. Okay, right, so if we have this expression, then we can now integrate. You can integrate this side and integrate that side. Okay, remember, anytime you are integrating, this is now a constant. This is a constant. If you have 1 over a certain number, look at it whether it's natural log, like we did initially. So this becomes natural log. So this will give us what? If you integrate this side, when we give us natural log, natural log of what? Q final minus what? Q. Okay, this is what we are having here. Okay, but of course we have to have this one between some limits. So Q to Q final, and this is going to, if you integrate this one, it's going to give us T over Ci. But remember, like the first one, we made it negative, but this is charging up, so that is where we have this point now. Right, so yes, so let's see. So at this point, okay, let's not get it well. Integrating this one, okay, this 1 over this, so it's not going to be that. It's not going to be straight away. So we're going to have the same expression Q F like we have here, minus Q here, but of course this is going to be negative because the minus sign is on the Q. Q is what we are differentiating with respect to, so this is going to be negative. Right, so let's clean this part so that we can have a very good expression. So we're going to repeat that one there and then do the integration. So this is the expression we have there. From here, this is what we have. We're going to have a negative plane. What our Q final minus our Q. Okay. As we have said, and then this is what we're going to be integrated, putting the values from 0 to the final Q, and this is equal to our T. This becomes T over CR. So let's see how we see T over CR. Now let's see how this will go. Right. Now this is going to give us what lane, putting in our values 0 for Q place. Okay. Q F minus the final, which is Q. Okay. Right, that is minus here. Put our minus sign there. Okay, so the first one is what we are putting in Q here. That's what we've done. Minus, okay. Then we're going to have the next one. Of course, because it is minus, the minus sign, you can put it in here so that if you want to. The first one is this minus, this is what we are getting. Minus, okay. So this is what we have here. Minus the second one that we are not going to substitute 0 in here. So minus QF minus 0. Right. We'll link this side as such. Okay, so this is a T over C. Let's click that up. So when it comes to integration, is refer to our mathematics integration. All this is discussed there. So T over CR. Now let's go. We have to watch the sign very well so that we don't mess up. So we're going to have natural log Q final minus Q here the constant. Now this is going to be minus. This is going to be bracket natural log Q final, right? So yeah, Q CR. So let's see the next natural log Q final minus Q. This becomes Q minus minus, so it becomes plus natural log Q final T over CR. But remember, this is a constant. This is a constant, right? It's a constant. So now let's multiply through by negative so that we get, if you multiply this, we eliminate this one. I'm going to get natural log Q final minus Q minus natural log Q final is equal to minus T CR. Right? Going? Good. Now we have natural log minus natural log. Log minus log is the same as the two is equal to division. Okay, so it's natural log of Q final minus Q over Q this is it. Because of the minus sign, you divide this one by that, and that is it. It's equal to negative G CR. So this is the equation that we arrived at. This is the equation that we arrived at. Okay, we can take anti-natural log of this expression. So we send this natural log there. Then we're going to get Q final plus Q over our Q final here is equal to e to the power. You raise one. Once you take natural log, this becomes the exponent minus T over CR. Right? So at this point, you can rearrange, okay? Your Q, this becomes your Q, final Q is equal to what? Q final E natural log T CR. Let's see whether we made any errors there. Let's go through and be careful. Right, so we are on the path. Now let's see. Let's make Q the subject. We are making Q the subject. Then this must cross the sign. This must cross the equal sign. Okay, and then we multiply through by negative so that we get Q to stand alone. Alright, so not to make it complex, let me clean the top one so that we can look at it well. So this is where we are now. So that is going to give us we have Q. We have Q